Okay, geometry, here we go. We're on section 12.3 now. The really good news for you guys is that we are actually getting pretty close to the end of the sections that we need to cover, so let's keep plugging away and let's finish strong right here. Okay, 12.3 is not as bad of a section or as long of a section as 12.2, but it's still kind of up there. And in 12.3, we're dealing with the concept of inscribed angles. And the English teacher inside of me waiting to get out really wants you guys to break this word down right here. The word scribe, anytime you hear that, means that something is written or drawn, and the prefix in kind of obviously means inside of something. So an inscribed angle, if you just break the name down, is something that's drawn inside. Now, that doesn't give you all the context, so let's go to the full definition right here. An inscribed angle is an angle whose vertex is on the circle itself and whose sides are chords of the circle. So if you take a look at this diagram that we've drawn right underneath here, we've got a circle here in blue, not a very good circle, but that's okay. And P is the vertex of our angle right there, and it is located on the circle itself. And then the sides of the angle right there are inside of the circle. They are chords. So we've got chord PQ right here and chord PR right underneath it. And together then that makes an angle right there, angle QPR. And that's our definition or our example of what an inscribed angle looks like. So that's a diagram we've got to get used to seeing. We got to be careful because this is different from what we were dealing with earlier in the chapter where we were dealing with central angles. And a central angle is formed by two radii of the circle, but the name kind of tells you where its vertex is. In a central angle, the vertex is located at the center, but over here now in an inscribed angle, our vertex is located on the circle itself. So that's the difference. We are not talking about central angles today, but instead we're focusing on inscribed angles. So that's our definition of inscribed angle. We have quite a few theorems to go along with it, but this is the big one right here, guys. Theorem 1211 says that the measure of an inscribed angle is half the measure of its intercepted arc. Okay, there's two different ways of expressing that here. The first one is the literal translation of the theorem we just read out. The measure of an inscribed angle is means equals here. There's your half, and then the measure of its intercepted arc. So if we take a look at this diagram over here, it kind of explains what's going on. We have an inscribed angle right here because its vertex is on the circle and its sides are both chords of the circle itself. And the measure of this inscribed angle is half the measure of this arc over here that it intercepts, or that is inside the chords of that angle right there. So what I decided to do here was to kind of work backwards and name this arc out here 2x degrees. And I thought it'd be easier then to ask you guys, okay, then what is half of 2x? And the answer to that would just be 1x. So then I kind of came backwards here and labeled the angle just plain x. We could have gone the other route, calling this right here x degrees, but then this would have been a 1/2 x, and people kind of prefer not to deal with fractions if they don't have to. The second way of expressing this exact same idea right here looks a little bit more like how we named it, but regardless, we just took the equation up here from the first one and multiplied both sides by 2. So 2 multiplied by the measure of your inscribed angle equals, well, if you multiply this 1/2 times arc times 2, the 1/2 and the 2 just cancel out, and you get the arc by itself. So if you're looking for just a quick little verbal way of remembering this, probably the second one is a little bit easier here, guys. That 2 times the measure of an inscribed angle is always going to equal the measure of the arc that it cuts off. Okay, so that's a big difference from what we were doing earlier, guys, where again, when we were dealing with central angles earlier in the chapter, if this was an n degree central angle, then the arc that it intercepts was just n as well. This was a 1-to-1 relationship here, but now things are changing, and with inscribed angles, it's a 1-to-2 relationship. That arc is always going to be twice as big as the angle that it intercepts. Okay, let's see that theorem in action here, guys. All right, so we have ourselves a circle. It looks like there are 3 points located on the circle right here, and we have ourselves an inscribed angle right here. Why is it inscribed? 2 reasons. Because its vertex is on the circle, and because the sides of that angle are chords of the circle, going here and here. Okay, and the theorem we just learned drew a relationship now between the measure of your central angle and the measure of the arc that is intercepted by that central angle. So to pull this off, we would now need to figure out the measure of that yellow arc right there. And of course, that's the one I didn't give you. Why? Because I'm kind of a jerk. But what I'm hoping you guys realize is that this entire circle is cut up into only 3 arcs, and 2 of them are given to you already. You've got an 80-degree arc right here and a 64-degree arc down there on bottom. And one of the important things to take away from this year, everybody, as you move on to next year is this. If you know how many pieces something has, and in this case, our circle has 3, if you know all but one of those pieces, you should be able to figure out the third one pretty quickly. So we would add together, actually what I'd probably do is grab my calculator and say that the entire circle is 360 degrees, and then subtract the 2 pieces we know, minus the 80 and minus the 64. And if I'm trying to do this in my head, the 80 and the 64 add up to 144 degrees, so that's going to leave us with 216 degrees, and that's the measure of this third arc. That's a major arc out here on the outside. And now that we know the 5x plus 8 and the 216, we can get going here. All right, we said there are 2 different ways of thinking about this theorem, but that probably the second one right here is the easier one. 2 times the measure of your inscribed angle equals the measure of the intercepted arc. 2 times the angle equals the arc. So step 1, let's write down our formula. 2 times the measure of your inscribed angle, which is 5x plus 8, equals the measure of the arc that it intercepts, which is 216 degrees. And that's the equation we need to solve now. Most of you, I would think, would want to distribute the 2 here. I would actually divide by the 2, but nobody in the world agrees with me. So we'll go 10x plus 16 is equal to 216. We'll subtract that 16 from both sides and get a nice round 200 over here on the right. And we'll divide by 10, and we'll come up with x is equal to 20. Now that's all the problem told us to do here, but if we wanted to check our answer, wouldn't be too tough. Let's try it. 5 times 20 right here is going to be 100, and 100 plus 8 is going to be 108 degrees. And sure enough, if you double that angle of 108, that's going to get you the 216 there that you needed for that arc. Okay, hopefully that one wasn't too tough. Let's take a look at example B, which is really the same concept, except now, instead of giving you just one variable expression here for the angle, there's another variable expression out here for the measure of the arc as well. But lucky for us, the concept is exactly the same. 2 multiplied by the inscribed angle is equal to the measure of the arc. So 2 multiplied by the inscribed angle of 3x minus 1 equals the measure of the intercepted arc, which is 5x plus 8. Now here, you really would have to distribute. I think that's really the only way to go here unless you want something really messy. So that's going to get us a 6x minus 2 is equal to a 5x plus 8. I would subtract 5x from both sides to get just an x over here on the left. I would add this 2 over to the right to get a 10 there, and I think that's it, guys. X is equal to 10. Let's double check that and see if that one works out. 3 times 10 for the angle here is 30, minus 1 gives us a 29-degree angle right here. 5 times 10 is 50, plus 8 is a 58-degree arc over here on the right side, and again, 29 times 2 equals that 58. So check, looks like we got this one right. Okay, let me just take a second right here before we move on any further and talk about a word here that we have occasionally discussed during the year, but not very often at all, and that word is corollary. And a corollary is kind of the third thing that goes along with postulates and theorems in geometry. So just like postulates and theorems, corollaries are mathematical facts that we know are true. Like theorems, they can be proven true. They're not like postulates, which we just go, oh yeah, but we can't really prove. The difference between a corollary and a theorem, though, is that a theorem is important enough really to be freestanding. A corollary is kind of this minor thing that just kind of latches on to an existing theorem and isn't important enough to exist on its own. I always think it's like a parasite, okay? But it's still true. So let's talk about it. A corollary says that in one circle, all inscribed angles that intercept the same arc are congruent. So what's going on here in this circle is I've drawn 2 points, A and B, and that gave us one minor arc over here that I'm highlighting in yellow that connects them. Now, I don't know the measure of that arc, but I'm going to go ahead and call that 2 n degrees. Okay, so we'll go with that. And now what this corollary deals with is inscribed angles that intercept that arc. So to draw that, it's not real complicated. I start at A. I draw a chord coming over here to some random point on the circle, and then I connect that random point to point B. And we just created an inscribed angle right here that intercepts arc AB. And since the measure of arc AB is 2n, let's go back to actually now the first writing of this. The measure of an inscribed angle is half the measure of its intercepted arc. So in this diagram, if the measure of arc AB is 2n degrees, we have to take half of that, and we'll get n degrees for the measure of this angle right there. Now, I'm really going to do the exact same thing again, but I'm going to choose a different point. So I tell you what, let me call that one point C, and I'll call this one here point D. And if I now make an inscribed angle with its vertex at point D that still intercepts the same arc AB, let's see what happens. So I'm going to draw in, I'm going to switch colors on you guys here. We're going to go to green for this one here. I'm going to draw in chord AD and then chord DB. And once again, we have an inscribed angle here that intercepts the same arc over here on the right that's still 2n degrees. So this inscribed angle here has to be half of 2n, which is going to be n as well. And let's try it one more time just for fun, everybody. Let's go to a weird color we don't use very often. How about a bright pink? All right, and for this one, I'm going to choose another point over here, and we'll call that point E. And now if I connect A to E, and then E back to B, there is yet another inscribed angle that intercepts the same arc of 2n degrees, so this angle has to be n degrees as well. And I'm going to stop right there because I think you guys get the point. All three of these angles, angle C, angle E, and angle D, they're all inscribed angles, and they all intercept this same arc over here on the right side, which has a measure of 2n degrees, so all of these angles have to be congruent to each other. And we could keep doing this all day with as many angles as we want, and boy, this gets tedious. You could draw that, and you could draw that, and that, and that, you know, something like that, but that gets a little annoying after a while. Anyway, no matter how many of those angles that we draw, they're all going to be congruent to each other. They're all going to have the same measure of n degrees. Okay, that was corollary number 1. Here's another corollary. Let's go with corollary number 2. So again, not important enough to be a freestanding idea right here, but it kind of latches on to the concept we were talking about earlier from the first theorem. This corollary says that an angle inscribed in a semicircle has to be a right angle. Now again, let's play English teacher right here. The prefix of semi, which we kind of use to mean partially, actually literally means half. So a semicircle is exactly half a circle. Now if we go back to this diagram here, remember that we're allowed to assume that a point that appears to be at the center of the circle is the center of the circle. So we can call this figure here circle P, meaning that P is the center. That means that if I were to say this was point A and this was point B right here, that line segment AB, well, it's clearly a chord because its endpoints are on the circle itself, but because it's a chord that passes through the center of the circle, we now know that AB is a diameter, and diameters cut a circle into 2 equal arcs. So we have a semicircle up here on the top of that circle. If I wanted to name that semicircle, if we remember way back to section 10.6, a semicircle should really be named with 3 points. So I'm going to call that point C right there. That means that in yellow, we have highlighted semicircle ACB. Okay, now what do we know? We know that AB is a diameter cutting right across the middle, and that means that a diameter cuts a circle in half. So we can now say that the measure of arc ACB is known to be 180 degrees. It's exactly half of that circle. Actually, I want to look at this another way right here. So if the measure of the yellow arc on top is 180 degrees, and the entire circle is 360, that means we also have a 180 degree arc down here on the bottom. It's impossible to have one semicircle without having a second. And now if we think about what's going on here, point C is located on the circle, and its sides are chords of the circle. That means that angle C up here is an inscribed angle, and the measure of an inscribed angle is 1/2 of the measure of the arc that it intercepts. So since angle ACB intercepts a 180-degree arc down here on bottom, we know that the measure of angle ACB has to be 90 degrees, which means, that is actually a right angle that needs to go right there. Okay, and that was something we didn't really intend, but is naturally going to happen. And I could do it again. If I picked another point over here on the bottom, I don't know, how about right here, and we just called that point D. If I drew chord AD, kind of hard to see, and then chord DB going right over here, this right there, guys, is yet another inscribed angle that intercepts a semicircle, a 180-degree arc. And that means that angle ADB has to be 90 degrees as well. And we could keep doing this all day long. Okay, so that was corollary 2. And corollary 3, the last one going along with this one right here, says the following, everybody, that the opposite angles of a quadrilateral inscribed in a circle have to be supplementary to one another. All right, so let's take a look at the diagram. There's a lot of vocabulary going on in this one right here. Obviously, we have ourselves a circle. And you'll notice then, guys, that I put 4 points on that circle, A, B, C, and D, and connected them in order to make a quadrilateral. A quadrilateral is just a 4-sided polygon. I don't know if it's a square or a rectangle or a parallelogram or a trapezoid or none of those things at all. We're just drawing it as a regular garden variety quadrilateral. And this corollary says that the opposite angles in this inscribed quadrilateral, like for example, angle A and angle C, would have to be supplementary. Let's talk about why that is. All right, if we focus on what's going on at angle BAD, the one that I have labeled X degrees, here is an angle with its vertex on the circle. That's an inscribed angle. And the arc that it intercepts, let's follow these segments over here, starts at B right here. And then let me go down from A to D and ends at D. So the arc intercepted by angle BAD is this arc all the way out here, guys. And if this inscribed angle is X degrees, then the measure of the arc that it forms needs to be twice as big as that. So that arc is going to have a measure of 2x degrees. Okay, I'm going to switch colors on you guys now to blue, and let's flip over now, and let's take a look at what's going on right over here at angle BCD, this angle right here, which we've labeled y degrees. Okay, going from point C, this chord shoots over here to B, so this creates an arc that starts here at B, and the other side goes over here and ends at D. So the arc created by angle C is this arc out here that I've got in blue. Now, if this inscribed angle is y degrees, the arc across from it needs to be twice as big. That's 2y degrees. And now if you take a look at the blue arc, that's 2y degrees, and the purple arc, that's going to be 2x degrees, if you look at those two together, ask yourself, how much of the entire circle do they make up? And the answer to that is all of it. So therefore, the sum of 2x plus 2y, together, they make up the entire circle, so that sum has to be 360 degrees. And now, we're just going to take advantage of a little fact we don't use too often, but the division property of equality says we can divide both sides of an equation by any number we want besides 0. And when we divide the entire left side by 2, what we're really doing is dividing each term individually here by 2. Okay, and when we do that, let's see what happens, guys. 2x divided by 2 is x, 2y divided by 2 is y, and 360 divided by 2 is 180. This corollary said that these two angles right here, the x and the y, had to be supplementary. And the definition of supplementary is two angles whose measures add up to 180 degrees. So that's kind of a quick informal proof of that particular corollary. All right, guys, let's see an example here that illustrates that one. Okay, so what are we dealing with right here, everybody? We have ourselves a circle, and I see 4 points located on that, and I hadn't labeled them before, but now, just so we know what we're talking about, I'm going to label those points A, B, C, and D. And since those points are connected in order, we have ourselves a quadrilateral that is inscribed inside of a circle. Okay, so with that in mind, that makes me realize that the last corollary, corollary 3 we just learned, is the one that's going to apply here. The opposite angles of a quadrilateral inscribed in a circle are supplementary. So you want to try to identify your opposite angles, and one pair of those, let's go green here, one pair of those would be angle A right up here, and then across from it, angle C. The corollary we just learned says that those two angles have to be supplementary. So we're going to take a 7x plus 11, and we're going to add to that its opposite angle, which is 5x plus 25, and that sum has to be 180 degrees. All right, let's solve that. The 7x and the 5x makes it 12x. 11 and 25 is 36. That equals 180. We'll subtract that 36 from both sides, and I believe get a 12x is equal to a 144 divided by 12. X is 12, and that's one of the two things we needed to do in this problem. But they also wanted us to solve for y, and the y's come from these angles over here. Angle D has a y, and so does angle B. There's a y there as well. But wouldn't you know it, once again, those are inscribed angles in a quadrilateral, so they have to be supplementary. So 8y plus 10 added to 20 minus 2y, that sum must be 180 as well. Okay, 8y minus 2y is going to get us a 6y, plus 10 plus 20 is a plus 30, and that's going to be 180. Subtract that 30 right there, we're going to get 6y is equal to 150, and then divided by 6, and I believe we're going to get y is equal to 25. All right, guys, so there's the answer for both x and y in that example. Okay, moving right along. Last theorem of this section here, guys, theorem 1212. So, it's because it's a new theorem and not a corollary, this one's a little separate from what we had been doing before, although it is still somewhat related. This one here says that the measure of an angle formed by a tangent, and remember, guys, that a tangent is always technically a line, the measure of an angle formed by a tangent and a chord is half the measure of its intercepted arc. Okay, so let's talk about that. Most chords, a line segment that cuts across a circle, like these that I'm drawing here in purple, are never going to touch your tangent line out here. The only way you can get a chord and a tangent to intersect is if they're drawn to the same point. T is the point of tangency of that tangent line, and so this only works if I draw a chord connecting it to that point right there. And this theorem says that the measure of the angle formed by the tangent and the chord. So our tangent line is out here on the bottom, the chord is LT, so we have an angle that's formed right here, and we're going to call that angle x degrees. So the measure of that angle formed is half the measure of its intercepted arc. And the intercepted arc, it goes between this tangent and this chord right over here. So the arc that we're talking about here, guys, is going to be minor arc LT right over here. The theorem then says that the measure of this angle formed is half the measure of arc LT, or look at it another way, arc LT is twice as big as this angle right here. So if that's x degrees, this would have to be 2x degrees. We kind of have the same thing happening over here on the other side of the figure. There's another angle formed by chord LT and tangent line MQ. That's this larger angle over here on the other side. I'm going to call that one y degrees. And that angle right there intercepts this big arc out here. That big arc needs to be twice as big as y, so this one is going to be 2y degrees. So, a couple of ideas, and I'm hoping you guys can see it from the diagram right here, that these two arcs, 2x and 2y, once again, make up the entire circle. So we know that 2x plus 2y, has to equal 360 degrees. And if we just divide everything in that equation by 2, we're going to get x plus y equals 180. Well, that's something I think you can see, because right here, this is going all the way back to the first week of geometry of the year, everybody. Those two angles right there, x and y, form a linear pair, and we know that angles that form a linear pair have to be supplementary. So we knew already that x plus y had to equal 180. So kind of two different ways of arriving at this conclusion tells us that it's pretty rock solid. All right, so that's not a proof, but that kind of illustrates why theorem 1212 works. And last thing we're going to do today, guys, one quick example to solve for x. So what's going on here, everybody? We've got ourselves a tangent line, okay, and then a chord drawn to the point of tangency. So theorem we just learned says that the measure of the angle formed right here, guys, between your tangent line and your chord is half the measure of the arc that it intercepts. Or probably the better way to do it would be that the arc formed is 2 times the measure of the angle. So kind of like we wrote down much earlier here, 2 multiplied by your angle is going to equal the measure of your arc. So 2 times the angle, which is 3x plus 51, has to equal the measure of the arc formed, which is 12x minus an 18. Again, most of you guys would distribute the 2 here. We get a 6x plus a 102 is equal to a 12x minus 18. We're going to subtract the 6x from both sides and get a 6x here on the right. We're going to add that 18 to both sides to get 120 over here on the left. Divide by the 6, and we're going to get x is equal to 20. All right, everybody. Still a long section right there, but better than 12.2. So that's a wrap on 12.3. Let's try that worksheet and let me know if you have any questions.